Welcome to Trek Through the Stars, a journey through the cosmos. For the next 2 hours, we will explore the Milky Way, our home galaxy, and the many extraordinary phenomena it contains. So sit back, relax, and if you enjoy this video and this type of content, hit the like button and subscribe for more content like this. Also, feel free to let me know in the comments if there's a topic you'd like to see covered in a future video. Above us, stretching across the night sky like a river of starlight, lies our cosmic home, the Milky Way. This vast spiral galaxy contains over 100 billion stars, each one a sun in its own right, many surrounded by worlds we have yet to discover. The Milky Way spans approximately 100,000 light-years from edge to edge. To comprehend this distance, imagine that light itself, traveling at 300,000 kilometers each second, would take 100,000 years to cross from one side of our galaxy to the other. Within this immense structure, our entire solar system occupies a space so small it would be invisible on any map of the galaxy. 4 great spiral arms sweep outward from the galaxy's center, like cosmic whirlpools frozen in time. These are the Perseus arm, the Sagittarius Carina arm, the Norma arm, and the Scutum Centaurus arm. Between the Perseus and Sagittarius Carina arms lies a smaller structure called the Orion arm, also known as the local arm, and this is where we find ourselves. Our Sun, along with its family of planets, rests approximately 26,000 light-years from the galactic center. We orbit this center at a leisurely pace of 220 kilometers per second, completing one full orbit every 225 million years. The last time Earth occupied this same position in space, dinosaurs ruled the planet. At the heart of our galaxy lies a region both magnificent and mysterious, the galactic bulge. Here, ancient stars crowd together in numbers beyond counting, their combined light creating a golden glow that astronomers can observe even through the dust that obscures our view. These are among the oldest stars in the galaxy, formed when the Milky Way was young, and the universe itself was barely a quarter of its current age. Recent observations have revealed that the Milky Way is not a perfect spiral. Instead, it possesses a central bar structure, a vast, elongated concentration of stars stretching across the galaxy's heart. This bar extends approximately 27,000 light-years from end to end and rotates slowly, taking hundreds of millions of years to complete a single turn. The gravitational influence of this bar helps to shape the spiral arms and guides the flow of gas and dust throughout the galaxy. The spiral arms themselves are not rigid structures like the spokes of a wheel. Rather, they are density waves, regions where stars and gas temporarily congregate before continuing their individual orbits around the galactic center. As material flows into these arms, it becomes compressed, triggering the birth of new stars. The brightest and most massive of these newborn stars illuminate the arms with their brilliant blue light, creating the spectacular spiral pattern we observe in other galaxies. Between the spiral arms lie vast spaces that might seem empty, but are filled with diffuse gas, ancient star clusters, and the scattered remnants of stellar explosions. Here, in these quieter regions of the galaxy, older stars like our Sun pursue their patient orbits, carrying with them the accumulated dust and metals forged in the nuclear furnaces of previous generations of stars. The galaxy's disk, where most of the stars reside, is surprisingly thin relative to its width, only about 1,000 light-years thick compared to its 100,000 light-year diameter. If the Milky Way were the size of a compact disc, its thickness would be comparable to a sheet of paper. Above and below this thin disc extends the galactic halo, a roughly spherical region containing the galaxy's oldest stars arranged in globular clusters. These ancient stellar cities, some containing over 1 million stars each, orbit the galactic center on highly elongated paths that carry them far from the disk and back again over hundreds of millions of years. The stars within these clusters formed when the galaxy was young, and their light carries the chemical signature of a simpler time when the universe contained mostly hydrogen and helium. Recent studies using data from the Gaia Space Telescope have revealed that our galaxy's structure is far more complex than once believed. The disk shows subtle warps and ripples, evidence of ancient gravitational encounters with smaller galaxies that were consumed by the Milky Way's inexorable pull. These cosmic archaeological clues tell the story of our galaxy's violent past and its continuing evolution. The Milky Way rotates in a stately fashion, but not as a solid body. Stars closer to the center complete their orbits more quickly than those at the edges, a phenomenon known as differential rotation. This creates a shearing effect that helps to maintain the spiral structure over billions of years, despite the fact that the galaxy has rotated many times since its formation. As we peer deeper into the structure of our cosmic home, we discover that the Milky Way is not an isolated island of stars. It is the dominant member of a small collection of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller companions. These galaxies dance together under the influence of their mutual gravitational attraction, and in approximately 4.5 billion years, the Milky Way and Andromeda will merge in a spectacular cosmic collision that will reshape both galaxies into something entirely new. The beauty of the Milky Way structure reveals itself to us in the patterns of starlight that arch across our night sky. On clear, dark nights, away from the glow of cities, we can see the galaxy's disk edge on, appearing as a bright band that encircles the heavens. This is the same spiral structure that astronomers observe in distant galaxies, seen from the unique perspective of beings living within it. In the direction of the constellation Sagittarius, the Milky Way appears brightest and most dense, for here we look toward the galaxy's center. Dark lanes of dust create intricate patterns against the background of stars, sculpting the light into shapes that have inspired human imagination for millennia. These dust lanes are not empty voids, but the birthplaces of future generations of stars, waiting for the gentle compression of a passing density wave to collapse them into new suns. The structure of the Milky Way continues to reveal its secrets as our instruments grow more sensitive and our understanding deepens. Each observation adds another piece to the cosmic puzzle, helping us to understand not only where we are in the universe, but how we came to be here, orbiting an ordinary star in an ordinary spiral arm of what we now know to be an extraordinary galaxy. Throughout the Milky Way, stars gather in communities that span the full range of cosmic architecture, from loose associations of young siblings to ancient cities containing millions of stellar inhabitants. These stellar congregations tell the story of how stars are born, how they live, and how they shape the galaxy around them. The youngest star clusters in our galaxy are the open clusters, loose collections of stars that form together from the same cloud of gas and dust. These stellar families typically contain anywhere from a few dozen to several thousand members, all sharing a common origin and a similar age. The Pleiades, visible to the naked eye as a tight group of bright blue stars in the constellation Taurus, represents one of the most famous examples of such a cluster. The Pleiades cluster, also known as the Seven Sisters, lies approximately 440 light-years from Earth and contains over 1,000 stars. Recent research suggests that this cluster, along with the nearby Hyades cluster and even the star-forming region of Orion, may have originated from the same primordial cloud of gas and dust that began collapsing some 60 million years ago. These stellar associations are still young by cosmic standards. Their brightest stars burn with the fierce blue-white light characteristic of massive, short-lived suns. Open clusters serve as cosmic laboratories where astronomers can study stellar evolution. Because all the stars in a cluster formed at approximately the same time and from material of similar composition, any differences between them result primarily from their varying masses. By studying the full range of stars within a cluster, from the most massive blue giants to the smallest red dwarfs, scientists can piece together the complete story of how stars age and change over time. The double cluster in Perseus presents a spectacular example of stellar youth and beauty. This pair of open clusters, visible to the naked eye as a hazy patch of light, contains hundreds of brilliant blue and white stars, many of them massive enough to end their lives in spectacular supernova explosions. The light from these clusters has traveled over 7,000 years to reach us, yet the stars themselves are only a few million years old, infants by astronomical standards. In stark contrast to these youthful open clusters stand the globular clusters, ancient spherical cities of stars that populate the galactic halo. These magnificent objects contain some of the oldest stars in the universe, formed when the Milky Way was young and the cosmos itself was less than 1 billion years old. Each globular cluster can house anywhere from 100,000 to over 1 million stars, packed into a sphere only 50 to 100 light-years across. Omega Centauri, the largest and brightest globular cluster visible from Earth, contains approximately 10 million stars crammed into a region smaller than the distance between our Sun and its nearest stellar neighbors. If Earth orbited a star within Omega Centauri, our night sky would be ablaze with thousands of stars brighter than Venus, creating a celestial dome of perpetual twilight. The stars within globular clusters are predominantly red and yellow, much older and cooler than the blue giants found in open clusters. These ancient suns have burned steadily for billions of years, converting hydrogen to helium in their cores with remarkable efficiency. Some contain so little of the heavier elements that they must have formed when the universe was still chemically simple, before generations of stellar death had enriched the cosmos with carbon, oxygen, silicon, and iron. Between these established stellar communities lie the stellar nurseries, vast clouds of gas and dust, where new stars continue to be born today. These regions, known as star-forming nebulae, represent some of the most dynamic and beautiful phenomena in the galaxy. Here, the gentle gravitational pull of dark matter and the compression waves from nearby supernovae conspire to collapse portions of the interstellar medium into dense knots that eventually ignite as new stars. The Orion Nebula, located approximately 1,500 light-years from Earth, serves as the closest large star-forming region to our solar system. This brilliant cloud of gas and dust spans dozens of light-years and glows with the combined light of over 2,000 young stars. At its heart lies the Trapezium cluster, a tight group of 4 massive blue stars whose intense radiation ionizes the surrounding gas, causing it to emit the characteristic red glow of hydrogen and the blue-green light of oxygen. Recent observations by the James Webb Space Telescope have revealed the Orion Nebula in unprecedented detail, showing the complex structures created by stellar winds and radiation pressure, towering pillars of dust rise from the nebula's surface like cosmic cathedrals, their shapes carved by the relentless outflow of particles from newborn stars. Within these pillars, astronomers have discovered evidence of planetary systems in formation, with disks of dust and gas slowly condensing into the building blocks of future worlds. The Eagle Nebula, immortalized by the Hubble Space Telescope's famous Pillars of Creation image, demonstrates the dramatic interplay between star formation and destruction. Here, massive stars, born from earlier episodes of collapse, now pump energy into their surroundings, simultaneously triggering new star formation, while eroding the very clouds that gave them birth. The pillars themselves are dense concentrations of gas and dust, their surfaces sculpted by radiation pressure into forms that resemble cosmic sculptures. Within these stellar nurseries, the process of star formation unfolds over millions of years. It begins when a portion of a molecular cloud becomes unstable, perhaps triggered by the shockwave from a nearby supernova or the gravitational influence of a passing star. As the cloud contracts under its own gravity, it begins to spin faster, flattening into a disk shape. At the center, matter accumulates until temperatures and pressures become high enough to ignite nuclear fusion, marking the birth of a new star. The youngest stars in these regions are often still surrounded by the remnants of their birth clouds, creating distinctive objects called T Tauri stars. These stellar infants are highly variable, flickering and flaring as they settle into the stable nuclear burning that will sustain them for billions of years. Many are accompanied by circumstellar disks of dust and gas, the raw material from which planetary systems form. The Rosette Nebula in the constellation Monoceros presents another magnificent example of ongoing star formation. This cosmic flower spans approximately 100 light-years and glows with the characteristic red light of hydrogen emission. At its center lies NGC 2244, a young cluster of hot, massive stars whose stellar winds have carved out a cavity in the surrounding gas. The nebula's distinctive shape results from the complex interaction between stellar radiation, magnetic fields, and the turbulent motions of the gas itself. Stellar associations represent looser collections of young stars that share a common origin but lack the gravitational binding that holds clusters together. The Scorpius-Centaurus association, the nearest such group to Earth, contains hundreds of young, hot stars scattered across dozens of degrees of sky. These stars form together, but have since begun to drift apart as they orbit the galactic center at slightly different speeds. The study of star clusters and stellar nurseries reveals the cyclical nature of stellar birth and death in the galaxy. Massive stars in young clusters live fast and die violently, enriching the interstellar medium with heavy elements created in their cores. These elements become incorporated into new generations of stars, slowly increasing the chemical complexity of the galaxy over cosmic time. The distribution of star-forming regions throughout the Milky Way follows the spiral arm structure, with most active star formation occurring within the density waves that define these magnificent cosmic curves. As gas and dust flow into the spiral arms, they become compressed and fragmented, triggering widespread star formation that illuminates the arms with the brilliant light of young, massive stars. Some stellar nurseries contain evidence of triggered star formation, where the death of one generation of stars compresses nearby gas clouds and initiates the birth of the next generation. This process creates expanding bubbles of hot gas, surrounded by rings of newly formed stars, linking the death and birth of stars in an endless cosmic cycle. The globular clusters, despite their great age, continue to evolve through complex gravitational interactions between their member stars. Close encounters can eject lower mass stars from the cluster core while concentrating more massive stars toward the center. This process, called mass segregation, gradually changes the structure of globular clusters over billions of years. Binary and multiple star systems are common within both open and globular clusters, forming when the gravitational collapse of a gas cloud fragments into multiple centers of condensation. These stellar partnerships can dramatically affect the evolution of their components, with mass transfer between companions leading to exotic phenomena such as X-ray bursts, novae, and eventually the formation of white dwarf stars, neutron stars, or black holes. The stellar nurseries of today will become the open clusters of tomorrow, their bright blue stars gradually burning out while their longer-lived red and yellow members continue to shine for billions of years. Eventually, the gravitational influence of the galaxy will disperse these clusters, sending their member stars on individual journeys around the galactic center, carrying with them the elements forged in stellar cores and the potential to form new planetary systems. In this way, the star clusters and stellar nurseries of the Milky Way represent both the past and future of our galaxy, archives of cosmic history written in starlight, and the workshops where tomorrow's stars and worlds are being crafted from the ashes of yesterday's stellar giants. Scattered throughout the Milky Way, like cosmic artwork painted on the canvas of space, nebulae represent some of the most breathtaking and scientifically significant phenomena in our galaxy. These vast clouds of gas and dust serve as both stellar nurseries and stellar graveyards, marking the places where stars are born and where they return their enriched material to the cosmos. The word nebula comes from the Latin term meaning cloud, and these celestial clouds span an extraordinary range of sizes, compositions, and origins. Some stretch across hundreds of light years, while others occupy regions smaller than our solar system. What unites them all is their role in the great cosmic cycle that transforms simple hydrogen and helium into the complex chemistry necessary for planets and life. Emission nebulae glow with their own light, energized by the intense radiation from nearby hot stars. The most abundant element in these regions is hydrogen, which absorbs ultraviolet light from massive blue stars and re-emits it as the characteristic red glow of hydrogen alpha radiation. This process, called fluorescence, transforms invisible ultraviolet energy into the visible light that makes these nebulae shine like cosmic beacons across interstellar space. The Rosette Nebula exemplifies the beauty and complexity of emission nebulae. Located approximately 5,000 light-years away in the constellation Monoceros, this cosmic flower spans nearly 100 light-years across. At its heart lies the open cluster NGC2244, whose massive stars pump tremendous amounts of energy into the surrounding gas. The stellar winds from these young giants have carved out a central cavity, creating the distinctive rosette shape that gives this nebula its name. The colors visible in the emission nebulae tell the story of their composition. Hydrogen produces the dominant red glow, while oxygen creates blue-green hues, and nitrogen contributes subtle red and violet tones. Sulfur adds yellow wavelengths to the mix, and when all these elements combine under different conditions of temperature and density, they create the rich palette of colors that makes each nebula unique. The Heart Nebula, officially designated IC1805, demonstrates how stellar winds sculpt the surrounding medium into complex structures. Located approximately 7,500 light-years from Earth, this nebula spans approximately 200 light-years. and contains several distinct regions of star formation. The intense radiation from young stars has compressed the surrounding gas into dense pillars and globules, some of which are collapsing to form the next generation of stars. Reflection nebulae present a different type of cosmic beauty. Rather than producing their own light, these clouds reflect and scatter the light from nearby stars, much as Earth's atmosphere scatters sunlight to create blue skies. The blue color predominates because shorter blue wavelengths scatter more efficiently than longer red wavelengths, a phenomenon first explained by Lord Rayleigh in his studies of atmospheric optics. The Witchhead Nebula, also known as IC2118, serves as a spectacular example of a reflection nebula. This ghostly blue cloud lies approximately 1,000 light-years away and reflects light from the bright star Rigel in the constellation Orion. The nebula's ethereal appearance results from the way dust grains within the cloud preferentially scatter blue light, creating an otherworldly glow that seems to drift through space like cosmic smoke. Dark nebulae represent regions where dense concentrations of dust block the light from stars beyond, creating silhouettes against the brighter background of the Milky Way. These apparently empty regions are actually among the most important sites in the galaxy, serving as reservoirs of material for future star formation. The dust within these clouds provides both the raw material for planetary systems and the thermal regulation necessary for gas clouds to collapse under their own gravity. The Horsehead Nebula stands as perhaps the most famous dark nebula in the sky. This distinctive silhouette, resembling the head and neck of a horse, appears against the bright backdrop of the emission nebula IC434 in the constellation Orion. The dark cloud contains enough material to form hundreds of stars, and infrared observations have revealed evidence of ongoing star formation hidden within its dusty embrace. The Coalsack Nebula, visible to the naked eye as a dark patch in the southern Milky Way, spans approximately 7 light-years and lies only 600 light-years from Earth. This relatively nearby dark cloud has played an important role in the mythology of Southern Hemisphere cultures, who saw in its shape various animals and celestial symbols. Modern astronomical studies have revealed that the Coalsack contains dense cores that may be on the verge of gravitational collapse, representing the earliest stages of star formation. Planetary nebulae, despite their name, have nothing to do with planets. These cosmic shells represent the final stages in the evolution of stars similar to our Sun. When such stars exhaust the hydrogen fuel in their cores, they expand into red giants before ejecting their outer layers into space. The hot, exposed core that remains ionizes the expanding shell of gas, creating some of the most geometrically perfect and colorful objects in the universe. The Ring Nebula in the constellation Lyra appears as a perfect smoke ring suspended in space, approximately 2,300 light-years from Earth. This planetary nebula formed when a dying star expelled its outer atmosphere in a series of gentle puffs, creating concentric shells of gas that now glow in the light of the central white dwarf star. The ring structure results from our viewing angle. We are looking down the axis of what is actually a 3-dimensional barrel or cylinder of glowing gas. The Helix Nebula, often called the Eye of God for its remarkable resemblance to a giant eye, represents one of the closest and largest planetary nebulae visible from Earth. Located approximately 700 light-years away, this nebula spans nearly 3 light-years across, making it appear about half the size of the full moon when viewed through a telescope. The complex braided structure visible in detailed images results from the interaction between fast and slow-moving gas ejected at different times during the star's death throes. Supernova remnants mark the sites where massive stars ended their lives in catastrophic explosions, enriching the interstellar medium with heavy elements forged in stellar cores and distributing enormous amounts of energy throughout their local neighborhoods. These expanding shells of hot gas continue to glow for thousands of years after the initial explosion, serving as cosmic laboratories for studying extreme physics and the dispersal of stellar material. The Crab Nebula represents the most studied supernova remnant in the sky. This expanding cloud of gas resulted from a stellar explosion observed by Chinese astronomers in the year 1054 CE, when it appeared as a guest star bright enough to see during daylight for several weeks. At the center of the nebula lies a pulsar, the rapidly spinning remnant of the exploded star, which rotates 30 times per second and sweeps beams of radiation across space like a cosmic lighthouse. The Veil Nebula complex in the constellation Cygnus showcases the long-term evolution of supernova remnants. This vast network of glowing filaments spans approximately 3 degrees of sky and represents the aftermath of a stellar explosion that occurred between 5,000 and 8,000 years ago. The shock wave from the explosion continues to plow through the interstellar medium, heating gas to millions of degrees and creating the delicate lace-like structures visible in modern telescopic images. Nebulae also serve as chemical laboratories, where complex molecules form in the cold depths of space. Within the dense cores of molecular clouds, temperatures drop to only a few degrees above absolute zero, allowing atoms to stick together and form increasingly complex compounds. Water, ammonia, methanol, and even organic molecules containing carbon have been detected in these cosmic chemistry sets. The Orion Molecular Cloud Complex represents one of the most active star-forming regions in our local galactic neighborhood. This vast structure extends far beyond the visible Orion Nebula, encompassing several distinct regions of star formation, connected by streams of molecular gas. Radio telescopes have mapped the distribution of carbon monoxide and other molecules throughout this complex, revealing the intricate structure of the material from which new stars and planetary systems form. Some nebulae display remarkable symmetry and structure that hint at the complex physical processes operating within them. The cat's eye. Nebula exhibits an intricate series of knots, jets, and symmetric features that suggest its central star experienced a series of explosive episodes as it shed its outer layers. These structures form on scales of hundreds of billions of kilometers, yet they maintain their shapes for thousands of years as they expand into space. The creation and destruction evident in nebulae operate on vastly different timescales. Star formation within molecular clouds unfolds over millions of years, as gravity slowly overcomes the thermal and magnetic pressure that supports the gas against collapse. In contrast, the formation of planetary nebulae occurs relatively quickly, with most of the stellar envelope being ejected within a few thousand years. Supernova explosions represent the most rapid and violent form of stellar death, releasing in seconds the energy that a star like our Sun will produce over its entire 10 billion year lifetime. The shock waves from these explosions can trigger star formation in nearby molecular clouds, linking stellar death to stellar birth in a continuous cycle that has operated throughout the galaxy's history. The colors and structures visible in nebulae also encode information about the physical conditions within these cosmic clouds. Temperature, density, magnetic field strength, and the presence of dust all influence the appearance of nebular emission. By analyzing the light from nebulae across different wavelengths, astronomers can map these conditions and understand the processes that shape these beautiful objects. Modern space telescopes have revolutionized our understanding of nebulae by observing them across the full electromagnetic spectrum. Infrared observations penetrate the dust that obscures visible light, revealing the warm dust and embedded protostars within molecular clouds. X-ray observations detect the hot gas heated by supernova shockwaves, while radio telescopes map the cold molecular gas that serves as the raw material for star formation. The nebulae scattered throughout the Milky Way represent nature's most magnificent demonstrations of the fundamental processes that govern stellar evolution and galactic chemical enrichment. They serve as both monuments to stars that have completed their life cycles and nurseries where new generations of stars and planets come into being, ensuring that the galaxy remains a dynamic, evolving system capable of supporting the complex chemistry necessary for life. In observing these cosmic clouds, we witness the materials from which we ourselves are made. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in stellar cores and dispersed into space through the beautiful and violent processes that create and destroy nebulae. We are, quite literally, made of star stuff, connected to the cosmos through the great recycling system that operates on scales both vast and intimate throughout our galactic home. In the depths of the Milky Way lurk objects so extreme that they challenge our understanding of physics itself. These are the remnants of the most massive stars, compressed into forms so dense that they warp space and time around them. Black holes and neutron stars represent the ultimate fate of stellar evolution, where matter exists in states impossible to recreate anywhere else in the universe. When a star more than 25 times the mass of our Sun exhausts its nuclear fuel, no force in nature can prevent its gravitational collapse. In less than a second, the star's core implodes, crushing matter to densities beyond comprehension. If the core's mass exceeds approximately 3 times that of our Sun, it will collapse into a black hole, a region of space where gravity has become so strong that nothing, not even light itself, can escape. The boundary around a black hole, known as the event horizon, marks the point of no return. For a black hole with the mass of our Sun, this boundary would lie only 3 kilometers from the center. Yet the supermassive black hole at the heart of our galaxy, Sagittarius A star, possesses an event horizon with a radius of approximately 12 million kilometers, nearly 20 times the distance from Earth to our Sun. Sagittarius A star stands as one of the most studied objects in astronomy, a gravitational monster containing approximately 4 million solar masses compressed into a region smaller than Mercury's orbit. Located 26,000 light-years from Earth in the direction of the constellation Sagittarius, this supermassive black hole serves as the gravitational anchor around which our entire galaxy rotates. Recent observations have provided unprecedented views of the environment surrounding Sagittarius A star. The Event Horizon Telescope, a planet-sized array of radio telescopes, captured the first direct image of the shadow cast by our galaxy's central black hole. This shadow appears as a dark region surrounded by a bright ring of glowing gas, heated to billions of degrees as it spirals toward the event horizon. The stars that orbit closest to Sagittarius follow paths that would be impossible in any other gravitational environment. Some of these stars, designated as S stars, follow highly elliptical orbits that carry them within a few billion kilometers of the black hole's event horizon. During their closest approaches, these stars reach speeds of nearly 7,000 kilometers per second, more than 2% the speed of light. One particular star, known as S62, holds the record for the closest approach to Sagittarius A star ever observed. At its nearest point, This star passes within only 120 astronomical units of the black hole, closer than the planet Pluto orbits our Sun. The extreme gravitational field at this distance causes effects predicted by Einstein's theory of general relativity, including the precession of the star's orbit and the gravitational redshift of its light. The study of these orbital motions provided some of the strongest evidence for the existence of the supermassive black hole and earned the 2020 Nobel Prize in Physics for astronomers Reinhard Genzel and Andrea Ghez. Their decades of patient observation revealed that only an object as massive and compact as a black hole could account for the extreme speeds and tight orbits of these stars. Black holes of stellar mass are far more numerous throughout the galaxy, but much more difficult to detect due to their smaller size and the absence of light emission. Astronomers estimate that the Milky Way contains approximately 100 million stellar mass black holes, most of them solitary objects drifting invisibly through space. These remnants of massive stars announce their presence only when they interact gravitationally with nearby matter or companion stars. Binary systems containing a black hole and a normal star create some of the most energetic phenomena in the galaxy. As the black hole strips material from its companion, the infalling matter forms an accretion disk that heats to millions of degrees and emits intense X-ray radiation. The system Cygnus X1, one of the first objects confirmed to contain a black hole, exemplifies this process as a 21 solar mass black hole feeds on material from a blue supergiant star. Neutron stars represent another extreme outcome of stellar death, formed when stars between 8 and 25 times the mass of our Sun explode as supernovae. The core that survives this explosion contains more mass than our Sun compressed into a sphere, only 20 to 24 kilometers across. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth, roughly the mass of Mount Everest. The surface gravity on a neutron star exceeds that of Earth by a factor of 200 billion. This means that an object dropped from a height of 1 meter would hit the surface traveling at approximately 7 million kilometers per hour. The intense gravitational field creates effects that would seem like science fiction in any other context, including gravitational time dilation that causes time to pass noticeably slower at the star's surface compared to distant locations. Many neutron stars announce their presence through rapid rotation and intense magnetic fields, creating objects known as pulsars. These cosmic lighthouses emit beams of radiation from their magnetic poles, which sweep across space as the star rotates. When these beams align with Earth, we detect regular pulses of radio waves, X-rays, or gamma rays with clockwork precision. The first pulsar discovered, designated PSRB 1919+21, rotates once every 1.337 seconds with a regularity that initially led astronomers to consider whether they might be detecting signals from an alien civilization. The incredible precision of pulsar timing, some millisecond pulses maintain accuracy rivaling atomic clocks, has enabled breakthrough discoveries including the first indirect detection of gravitational waves. The fastest spinning pulsar known, PSRJ 1748-2446 AD, rotates 716 times per second. This neutron star spins so rapidly that its equatorial surface moves at approximately 24% the speed of light, approaching the theoretical limit for neutron star rotation. Beyond this limit, the centrifugal force would overcome gravity and tear the star apart. Magnetars represent the most magnetically powerful objects in the universe, with magnetic field strengths trillions of times stronger than Earth's magnetic field. These highly magnetized neutron stars occasionally release enormous bursts of energy that can be detected across the galaxy. A magnetar flare occurring within 10 light-years of Earth would prove fatal to most life on our planet. Fortunately, no known magnetars exist within this dangerous radius. The magnetic fields around magnetars are so intense that they fundamentally alter the properties of matter itself. In these extreme environments, atoms become elongated into needle-like shapes, and the normal rules of atomic physics break down. The energy stored in a magnetar's magnetic field exceeds the amount of energy our Sun will produce over its entire lifetime. Recent gravitational wave detections have opened a new window into the lives and deaths of neutron stars and black holes. The LIGO and Virgo observatories have detected the gravitational waves produced when these dense objects spiral into each other and merge, creating ripples in space-time itself that propagate across the universe at the speed of light. The collision of two neutron stars detected in both gravitational waves and electromagnetic radiation in August 2017 provided the first direct evidence for the cosmic origin of many heavy elements. This event, designated GW170817, created a kilonova explosion that synthesized gold, platinum, uranium, and other elements through rapid neutron capture processes impossible to achieve in any other astrophysical environment. Intermediate mass black holes occupy the gap between stellar mass and supermassive black holes, containing hundreds to thousands of solar masses. While their existence has been theoretically predicted, confirming their presence has proven challenging. Recent observations suggest that some globular clusters may harbor intermediate mass black holes at their centers, formed through the collision and merger of multiple stellar mass black holes. The formation mechanisms for supermassive black holes like Sagittarius A star remain one of astronomy's greatest puzzles. These objects appear to have existed when the universe was very young, suggesting they formed through processes different from stellar collapse. Possible mechanisms include the direct collapse of massive gas clouds in the early universe, or the rapid growth of smaller black holes through accretion and mergers. Black hole jets represent some of the most powerful phenomena in the universe, accelerating particles to nearly the speed of light and extending across millions of light years. While Sagittarius A star currently shows only modest activity, evidence suggests it experienced much more violent episodes in the past, when increased accretion rates powered jets that influence star formation throughout the galaxy. The study of black holes and neutron stars continues to push the boundaries of our understanding of fundamental physics. These objects provide natural laboratories for testing theories under conditions of extreme gravity, density, and magnetic field strength that cannot be replicated on Earth. They serve as cosmic particle accelerators, windows into quantum gravity, and the ultimate recyclers of stellar material. Recent theoretical work suggests that black holes may not be the permanent prisons they were once thought to be. Stephen Hawking's discovery of black hole radiation implies that these objects slowly evaporate over enormous timescales, eventually returning their contents to the universe. For stellar mass black holes, this process would take longer than the current age of the universe, while primordial black holes from the early cosmos might evaporate more rapidly. The detection of gravitational waves has confirmed many predictions about black hole behavior, including Stephen Hawking's area theorem, which states that the total surface area of black holes can never decrease. This verification represents a triumph of theoretical physics and demonstrates the power of these extreme objects to test our understanding of the universe's fundamental laws. As we continue to study these remarkable objects, black holes and neutron stars remind us that the universe operates according to principles far stranger and more wonderful than everyday experience suggests. They represent the ultimate expression of gravity's power and the final chapter in the lives of the most massive stars, while simultaneously serving as the engines that power some of the most energetic and beautiful phenomena in the cosmos. Drifting through the darkness between the stars, invisible wanderers pursue solitary paths through the galaxy. These are the rogue planets, worlds that have been ejected from their birth systems or formed in isolation, destined to spend eternity in the cold depths of interstellar space. Alongside these homeless worlds, an even more mysterious component pervades the galaxy: dark matter, an invisible substance that outweighs all visible matter by a factor of 5 to 1. Rogue planets, also known as free-floating planets or orphan worlds, represent one of the most intriguing populations of objects in the Milky Way. These planet-sized bodies travel through space unbound to any star, having either formed in isolation from collapsing gas clouds or been gravitationally ejected from their original planetary systems during chaotic encounters with other planets or passing stars. Current estimates suggest that rogue planets may outnumber stars in our galaxy, with some models predicting billions or even trillions of these wandering worlds. The exact number remains uncertain because rogue planets emit no light of their own and reflect no starlight, making them nearly impossible to detect except under very specific circumstances. The detection of rogue planets relies primarily on gravitational microlensing, a phenomenon predicted by Einstein's theory of general relativity. When a rogue planet passes directly between Earth and a more distant star, its gravitational field acts as a lens, briefly magnifying the background star's light. These events typically last only hours or days, requiring dedicated survey telescopes to monitor millions of stars simultaneously. One of the most intriguing rogue planet candidates discovered through microlensing is OGLE 2016 BLG 1928, an object with an estimated mass similar to Earth. This wandering world lies approximately 4,000 light-years from our solar system and appears to drift through space without any stellar companion. The brief gravitational lensing event that revealed its existence lasted only 42 minutes, highlighting the challenges inherent in studying these elusive objects. Some rogue planets may retain enough internal heat to support subsurface oceans, even in the absence of stellar radiation. Radioactive decay within their cores, combined with tidal heating from any large moons they might possess, could maintain liquid water beneath thick ice shells for billions of years. This raises the intriguing possibility that some rogue planets might harbor life in their hidden oceans, completely independent of any star. Jupiter-mass rogue planets might retain substantial atmospheres and emit enough infrared radiation from their formation heat to be directly detectable by sensitive space telescopes. Several candidates have been identified through infrared surveys, though confirming their rogue status requires ruling out the presence of extremely distant or faint stellar companions. The formation mechanisms for rogue planets fall into two main categories: ejection from planetary systems and direct formation from gas clouds. Computer simulations of planetary system evolution suggest that gravitational interactions between giant planets commonly lead to the ejection of one or more worlds, particularly during the early chaotic phase when planetary orbits are still settling. The NICE model, which describes the migration of giant planets in our own solar system, suggests that Uranus and Neptune migrated outward from their original positions closer to the Sun. This migration likely scattered numerous smaller bodies, including potential planetary embryos, that could have become rogue planets if ejected completely from the solar system. Direct formation of rogue planets from the collapse of small molecular cloud cores represents an alternative pathway that could produce isolated worlds without requiring ejection from planetary systems. These objects would form through the same basic process as brown dwarf stars, but with insufficient mass to sustain nuclear fusion, creating planet-sized objects that never experienced stellar companionship. Brown dwarfs, sometimes called failed stars, occupy the mass range between the heaviest planets and the lightest stars. These objects form like stars through gravitational collapse, but lack sufficient mass to maintain hydrogen fusion in their cores. With masses ranging from approximately 13 to 80 times that of Jupiter, brown dwarfs slowly cool and fade over billions of years, representing a bridge between planetary and stellar physics. Some brown dwarfs may host planetary companions, creating bizarre systems where a planet orbits an object that itself failed to become a star. These systems challenge our traditional definitions of planets and stars, existing in a grey area between conventional planetary systems and binary star systems. Dark matter represents an even more mysterious component of the galaxy, detectable only through its gravitational effects on visible matter and light. This invisible substance comprises approximately 27% of the universe's total mass energy, compared to less than 5% for ordinary matter made of atoms. The evidence for dark matter's existence comes from multiple independent observations. Galaxy rotation curves show that stars in the outer regions of spiral galaxies move too quickly to be held in orbit by the gravitational attraction of visible matter alone. Gravitational lensing observations reveal how dark matter bends light from distant galaxies, creating distorted images that map the distribution of this invisible mass. Within the Milky Way, dark matter forms an extended halo that encompasses the galaxy's visible disk and extends far beyond the orbit of the most distant stars. This dark matter halo contains approximately 10 times more mass than all the visible stars, gas and dust combined, making it the dominant gravitational component of our galactic home. Computer simulations of galaxy formation suggest that dark matter halos contain numerous smaller substructures, sometimes called dark matter clumps or subhalos. These invisible concentrations of mass may trigger tidal effects on nearby stars, or influence the formation and evolution of stellar streams, created when small galaxies are disrupted by the Milky Way's gravity. The nature of dark matter remains one of the greatest unsolved problems in modern physics. Leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, all hypothetical particles that interact with ordinary matter primarily through gravity. Despite decades of searches using increasingly sensitive detectors, dark matter particles have not been directly detected. Alternative theories propose that dark matter might not consist of particles at all, but rather represent a modification of gravity itself on large scales. These modified Newtonian dynamics, MOND theories, attempt to explain galaxy rotation curves and other dark matter evidence through changes to gravitational physics rather than invoking invisible matter. The distribution of dark matter within the galaxy influences the motion of everything from individual stars to entire globular clusters. High-velocity stars that appear to be escaping the galaxy's gravitational pull provide clues about the dark matter halo structure and total mass. Some of these hypervelocity stars may have been accelerated by close encounters with the supermassive black hole at the galactic center. Dark matter may also play a role in the formation and evolution of the galaxy's spiral structure. The gravitational influence of dark matter substructures could help maintain the spiral arms over billions of years, providing the density perturbations necessary to trigger ongoing star formation as the galaxy rotates. Recent observations using the Gaia Space Telescope have revealed evidence for the galaxy's violent past, including stellar streams and tidal tails created when smaller galaxies were torn apart by the Milky Way's gravity. These structures provide information about both the visible and dark matter components of our galaxy, helping astronomers map the three-dimensional distribution of mass throughout the galactic halo. The local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, exists within an even larger dark matter structure called the local sheet. This vast cosmic web of dark matter filaments and voids shapes the large-scale structure of the universe and determines the motion of galaxy groups across hundreds of millions of light years. Dark matter annihilation or decay could potentially produce detectable signatures in the form of gamma rays, neutrinos, or other particles. Indirect dark matter searches focus on regions of high dark matter density, such as the galactic center or nearby dwarf galaxies, looking for excess emission that could indicate dark matter interactions. The interplay between dark matter and ordinary matter influences star formation rates throughout the galaxy. Dark matter provides the gravitational scaffolding that concentrates gas into dense clouds, while feedback from star formation and supernova explosions can redistribute both types of matter on galactic scales. Primordial black holes, formed from density fluctuations in the early universe, represent another candidate for dark matter. These ancient black holes could have masses ranging from microscopic to thousands of solar masses, and their gravitational effects would be indistinguishable from particle dark matter in most astronomical observations. The cosmic microwave background radiation provides additional evidence for dark matter's existence and properties. The precise pattern of temperature fluctuations in this ancient light reveals how dark matter and ordinary matter behaved when the universe was only 380,000 years old, providing crucial constraints on dark matter theories. Future space missions and ground-based surveys will dramatically improve our understanding of both rogue planets and dark matter. The Roman Space Telescope will conduct extensive microlensing surveys capable of detecting Earth-mass rogue planets throughout the galaxy, while next-generation dark matter detectors will probe ever deeper into the realm of weakly interacting particles. The study of rogue planets and dark matter reminds us that the universe contains far more than meets the eye. These hidden components, one consisting of familiar matter in unexpected places, the other representing entirely unknown physics, shape the structure and evolution of galaxies while remaining largely invisible to direct observation. They challenge our understanding of planetary formation, stellar dynamics, and fundamental physics, ensuring that the cosmos retains its capacity to surprise and humble us with its complexity and mystery. Beyond the familiar realm of stars, planets, and nebulae, the Milky Way hosts some of the most extreme and energetic events in the universe. These cosmic phenomena unfold on scales of time and energy that dwarf human experience, representing the universe's capacity to concentrate enormous amounts of matter and energy into brief, brilliant displays that can be detected across billions of light years. Gamma-ray bursts stand among the most powerful explosions known to science, releasing more energy in seconds than our sun will produce over its entire 10 billion-year lifetime. These cosmic flashbulbs appear randomly across the sky, blazing briefly in gamma rays before fading to afterglows visible in X-rays, optical light, and radio waves. For a few moments, a single gamma ray burst can outshine the combined light of all the stars in the observable universe. Long-duration gamma ray bursts, lasting more than 2 seconds, appear to result from the collapse of extremely massive stars into black holes. These hypernova explosions occur when stars at least 25 times more massive than our Sun exhaust their nuclear fuel and undergo catastrophic core collapse. The resulting black hole launches powerful jets of material at nearly the speed of light, and when these jets align with Earth's direction, we observe them as gamma-ray bursts. Short-duration gamma-ray bursts, lasting less than 2 seconds, arise from entirely different circumstances. These brief flashes result from the collision and merger of 2 neutron stars, or a neutron star, and a black hole. The 2017 detection of gravitational waves from colliding neutron stars, followed 90 seconds later by a short gamma-ray burst from the same location, provided direct confirmation of this connection. The afterglow of a gamma-ray burst can remain visible for weeks or months as the initial blast wave plows through the surrounding interstellar medium. These afterglows have enabled astronomers to identify the host galaxies of gamma-ray bursts and determine their distances, revealing that these events occur throughout the observable universe, with some originating from galaxies billions of light-years away. Fast radio bursts represent another category of cosmic mystery that has only recently been recognized. These intense pulses of radio waves last mere milliseconds, but carry enormous amounts of energy. A single burst can release as much energy in radio waves as our Sun produces across all wavelengths in an entire day. Most fast radio bursts appear to originate from distant galaxies, though their exact nature remains hotly debated. The first repeating fast radio burst, discovered in 2016, provided crucial clues about these phenomena. Unlike the majority of fast radio bursts, which appear only once and never repeat, this source produced dozens of additional bursts over several years. The precise localization of its position revealed a host galaxy 3 billion light-years away, ruled out some theoretical models for fast radio burst origins. Magnetars, the most highly magnetized neutron stars in the universe, have emerged as leading candidates for fast radio burst sources. These objects possess magnetic fields trillions of times stronger than Earth's, and their occasional violent magnetic field rearrangements can produce brief but intense bursts of radiation across the electromagnetic spectrum. In 2020, astronomers detected the first fast radio burst from within our own galaxy, originating from the magnetar SGR 1935 + 2154. This burst was accompanied by X-ray and gamma-ray emission, providing the first direct evidence linking magnetars to fast radio burst production. If this burst had occurred in a distant galaxy, it would have appeared identical to the extragalactic fast radio bursts that have puzzled astronomers for over a decade. Gravitational waves represent perhaps the most exotic form of cosmic phenomenon, consisting of ripples in the fabric of space-time itself. These waves travel at the speed of light, carrying information about some of the most violent events in the universe. Unlike electromagnetic radiation, gravitational waves pass through matter almost unimpeded, providing a completely new way to observe cosmic phenomena. The first direct detection of gravitational waves in September 2015 marked the beginning of gravitational wave astronomy. The signal, designated GW150914, resulted from the merger of 2 black holes approximately 36, and 29 times the mass of our Sun, located 1.3 billion light-years from Earth. The collision lasted only a fraction of a second, but released more energy in gravitational waves than the combined light output of all the stars in the observable universe. Since that historic first detection, gravitational wave observatories have identified hundreds of black hole mergers, neutron star collisions, and other exotic events. Each detection provides information about the masses, spins, and distances of the merging objects, building a census of compact objects throughout the universe and testing Einstein's theory of general relativity under the most extreme conditions. The collision of neutron stars produces gravitational waves with characteristics distinct from black hole mergers. Neutron star mergers generate longer-lasting signals that encode information about the exotic matter within these ultra-dense objects. The tidal deformation of neutron stars during the final moments before merger provides insights into the equation of state of matter at nuclear densities. Neutron star mergers also serve as cosmic element factories, synthesizing heavy elements through rapid neutron capture processes. The radioactive decay of these newly formed elements powers kilonova explosions, creating optical and infrared transients that can be observed for weeks after the initial merger. These events represent the primary source of gold, platinum, and other precious metals in the universe. Pulsars, rapidly rotating neutron stars with intense magnetic fields, create some of the most precise timekeepers in the universe. The lighthouse-like beams of radiation they emit sweep across space with clockwork regularity, allowing astronomers to detect tiny variations in their arrival times at Earth. These timing variations can reveal the presence of gravitational waves passing between the pulsar and Earth. Arrays of precisely timed pulsars throughout the galaxy serve as natural gravitational wave detectors, sensitive to much lower frequencies than ground-based observatories can detect. These pulsar timing arrays are searching for gravitational waves from supermassive black hole mergers and other phenomena that produce longer wavelength signals lasting months or years. The most rapidly spinning pulsar known, PSRJ 1748-2446 AD, rotates 716 times per second, approaching the theoretical limit for neutron star rotation. At this rate, the stellar surface moves at approximately 1/4 the speed of light, creating extreme conditions where general relativistic effects become significant and the boundaries between different states of matter blur. Millisecond pulsars represent an evolved population of neutron stars that have been spun up through accretion from binary companions. These cosmic clocks maintain timing precision, rivaling the best atomic clocks on Earth, making them invaluable tools for testing fundamental physics and searching for gravitational waves. Some pulsars exhibit sudden changes in their rotation rates, called glitches, which provide insights into the internal structure of neutron stars. These events may result from interactions between the neutron star's solid crust and its superfluid interior, representing phenomena that cannot be studied in any terrestrial laboratory. High-energy cosmic rays, particles accelerated to energies far exceeding those achievable in human-built accelerators, constantly bombard Earth from sources throughout the galaxy and beyond. The most energetic cosmic ray particles carry energies equivalent to a baseball traveling at highway speeds, concentrated in a single atomic nucleus. Supernova remnants serve as cosmic particle accelerators, using shock waves to boost particles to enormous energies through a process called diffusive shock acceleration. As these shock waves propagate through the interstellar medium, They encounter magnetic field irregularities that repeatedly scatter particles back and forth across the shock front, gradually increasing their energies to relativistic speeds. The knee in the cosmic ray energy spectrum, occurring at approximately 10 to the 15th electron volts, likely marks the energy limit for galactic sources such as supernova remnants. Beyond this energy, cosmic rays probably originate from extragalactic sources such as active galactic nuclei, gamma-ray bursts, or other exotic phenomena. Ultra-high energy cosmic rays, with energies exceeding 10 to the power of 19 electron volts, represent the most extreme particles known to science. These rare events occur only once per square kilometer per century, requiring enormous detector arrays spread across thousands of square kilometers to collect sufficient statistics for study. The interaction of cosmic rays with the interstellar medium produces secondary particles, including gamma rays, neutrinos, and antimatter particles. These secondary products provide indirect evidence for cosmic ray acceleration sites and help map the distribution of cosmic rays throughout the galaxy. Cosmic ray interactions in Earth's atmosphere create extensive air showers containing billions of secondary particles that can be detected at ground level. These showers provide information about the energy, composition, and arrival direction of the primary cosmic ray, allowing astronomers to trace the most energetic particles back toward their sources. Neutrinos, nearly massless particles that interact only weakly with matter, provide another window into high-energy astrophysical phenomena. These ghostly particles can travel through the entire Earth without interacting with a single atom, carrying information from the cores of stars, supernovae, and other extreme environments. The IceCuber Neutrino Observatory, buried deep in Antarctic ice, has detected neutrinos from sources throughout the universe, including blazars, active galactic nuclei with jets pointed toward Earth. These observations represent the birth of multi-messenger astronomy, where gravitational waves, electromagnetic radiation, and neutrinos provide complementary information about cosmic phenomena. Solar neutrinos, produced by nuclear fusion in the Sun's core, arrive at Earth in vast numbers. Trillions pass through every square centimeter of Earth's surface each second. The detection and study of these neutrinos has provided crucial confirmation of our understanding of stellar nuclear processes and revealed unexpected properties of neutrinos themselves. Supernova neutrinos carry away approximately 99% of the energy released during core collapse, making them the dominant energy output of these explosions. The 1987 detection of neutrinos from supernova, 1987A in the Large Magellanic Cloud, provided direct evidence for the core collapse mechanism and marked the beginning of neutrino astronomy. These cosmic phenomena collectively demonstrate that the universe operates according to physical principles, far more extreme than anything we encounter in everyday life. They represent natural laboratories for testing fundamental physics under conditions of temperature, density, energy, and gravitational field strength that cannot be replicated on Earth, pushing our understanding of the universe to its very limits, while revealing the remarkable creativity of nature in manifesting the laws of physics across the cosmos. As we gaze into the depths of space and time, contemplating the vast cycles that govern our cosmic home, we can glimpse the destiny that awaits the Milky Way across the eons to come. The future of our galaxy unfolds on timescales so vast that they dwarf human history, yet the fundamental processes we observe today will continue to shape this cosmic story for billions of years into the future. The most dramatic event in the Milky Way's future lies approximately 4.5 billion years ahead, when our galaxy will collide and merge with the Andromeda Galaxy. This cosmic encounter will fundamentally reshape both galaxies and create an entirely new galactic structure that astronomers have already nicknamed Milky Way. Currently, the Andromeda Galaxy approaches us at approximately 110 kilometers per second, closing the gap across the 2.5 million light-years that separate our galactic centers. Despite this seemingly modest speed, the inexorable pull of gravity ensures that this collision is inevitable, representing the culmination of a cosmic dance that began billions of years ago when both galaxies first formed within the same dark matter structure. The merger will unfold over several billion years as the two spiral galaxies first pass through each other, then wheel around for successive encounters before finally settling into a single, larger elliptical galaxy. Computer simulations suggest that during the initial approach, gravitational forces will distort both galaxies, stretching their spiral arms into long tidal tails and triggering massive bursts of star formation as gas clouds throughout both systems collide and compress. Despite the violence implied by the term galactic collision, the vast spaces between individual stars mean that direct stellar collisions will remain extremely rare. Our Sun and its planets will likely survive the merger intact, though they may be flung into a completely different region of the combined galaxy. Some simulations suggest that our solar system could be ejected into the galactic halo or even into intergalactic space, while others show it settling into a stable orbit within the merged system. The supermassive black holes at the centers of both galaxies, Sagittarius, a star in the Milky Way, and its larger counterpart in Andromeda, will eventually spiral toward each other and merge into a single, even more massive black hole. This process will generate gravitational waves of unprecedented intensity, though by that time, the waves will propagate through a universe much larger and more diffuse than today. Long before the Andromeda collision, the Milky Way will undergo significant internal evolution driven by the ongoing consumption of its gas supply and the aging of its stellar population. Star formation rates throughout the galaxy have been declining for several billion years and will continue to drop as the raw materials for new stars become increasingly scarce. The galaxy currently converts approximately 2 solar masses of gas into new stars each year, but this rate has decreased substantially from its peak billions of years ago. As massive stars continue to explode as supernovae, they enrich the interstellar medium with heavy elements while simultaneously driving gas out of the galactic disk through powerful stellar winds and supernova shockwaves. Within the next 5 billion years, star formation in the Milky Way may decline to negligible levels, transforming our galaxy from a vibrant spiral into a more quiescent system dominated by aging red and yellow stars. The brilliant blue giants that currently illuminate the spiral arms will have long since exhausted their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes as silent monuments to their former glory. Our own sun will play a role in this cosmic evolution, though its individual contribution remains modest compared to the galaxy-wide processes. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant star. During this phase, it will expand to perhaps 100 times its current size, engulfing the orbits of Mercury and Venus and rendering Earth uninhabitable. Eventually, the sun will shed its outer layers in a series of gentle puffs, creating a planetary nebula that will glow for thousands of years before fading. The remaining white dwarf core will slowly cool over trillions of years, gradually dimming from white-hot to red, then to a cold, dark ember invisible except for its gravitational influence. The fate of stellar remnants throughout the galaxy depends on their masses and compositions. White dwarf stars, the most common stellar endpoints, will cool slowly over timescales, exceeding the current age of the universe many times over. In approximately 10 to the 15th years, a quadrillion years, even the longest-lived white dwarfs will have cooled to match the temperature of the cosmic microwave background radiation. Neutron stars and black holes represent more exotic endpoints that will persist far longer than white dwarfs. Neutron stars may gradually lose their rotational energy and magnetic fields over cosmic time, eventually becoming cold, dark objects detectable only through their gravitational effects. Black holes, according to Stephen Hawking's calculations, will slowly evaporate through quantum effects. But this process requires timescales of 10 to the 67th years for stellar mass black holes, incomprehensibly longer than the current age of the universe. The evolution of the Milky Way's dark matter halo will parallel these changes in the visible components. Computer simulations suggest that dark matter halos continue to grow through accretion and mergers with smaller structures, gradually becoming more massive and extended over cosmic time. The merger with Andromeda will combine the dark matter halos of both galaxies, creating an even larger gravitational structure. Smaller satellite galaxies orbiting the Milky Way will gradually spiral inward and be consumed through tidal disruption, adding their stars and dark matter to our galaxy's mass. This process of galactic cannibalism has been ongoing throughout the Milky Way's history and will continue for billions of years, slowly building the galaxy's mass while erasing the individual identities of its smaller companions. The Large and Small Magellanic Clouds, our galaxy's most prominent satellites, will likely be accreted within the next few billion years. Computer models suggest that these irregular galaxies are on their first passage around the Milky Way and will eventually be tidally disrupted, contributing their gas, stars, and dark matter to our galaxy's structure while creating spectacular stellar streams visible across the sky. Climate change on cosmic scales will affect the entire galaxy as the universe continues to expand and cool. The cosmic microwave background radiation, currently at a temperature of 2.7 degrees above absolute zero, will continue to cool as the universe expands, eventually reaching temperatures so low that it provides no significant energy input to any astrophysical processes. The expansion of the universe will gradually separate galaxy groups and clusters from each other, making intergalactic space increasingly empty and cold. The local group, bound together by gravity, will resist this expansion and eventually collapse into a single merged galaxy. But more distant galaxies will recede beyond the observable horizon and effectively disappear from our cosmic neighborhood. Star formation throughout the universe will gradually decline as gas supplies become exhausted and existing gas is locked away in stellar remnants or ejected from galaxies entirely. The era of active star formation may end within 10 to the power of 12 to 10 to the power of 14 years, after which the universe will enter what cosmologists call the degenerate era, dominated by white dwarfs, neutron stars, and black holes. During this distant epoch, the merged remnant of the Milky Way and Andromeda will consist primarily of stellar remnants orbiting in ever-changing configurations. Gravitational interactions between these objects will occasionally eject some remnants from the galaxy entirely, while causing others to fall toward the central supermassive black hole. The ultimate fate of the galaxy depends on several factors that remain uncertain in current physics. If protons are truly stable particles, stellar remnants will persist for unimaginably long periods, slowly cooling until they reach thermal equilibrium with the cosmic microwave background. However, some theories predict that protons may decay with half-lives of approximately 10 to the 34th years, which would gradually dissolve all matter into lighter particles and energy. The cosmic web of dark matter that currently connects galaxies across hundreds of millions of light-years may also evolve in unexpected ways. Some theories suggest that dark matter particles might interact with each other or decay over cosmic time, potentially altering the large-scale structure of the universe in ways we cannot currently predict. Black holes will become increasingly important as other energy sources fade. The supermassive black hole at the center of the merged galaxy may continue to grow by accreting stellar remnants and any remaining gas, while stellar mass black holes throughout the galaxy will slowly evaporate through Hawking radiation. Paradoxically, smaller black holes evaporate faster than larger ones, so stellar mass black holes will disappear long before supermassive black holes. The possibility of intelligent life persisting through these cosmic changes remains an open question that ventures into the realm of speculation. Any technological civilization surviving these timescales would need to develop strategies for harnessing energy from increasingly exotic sources, such as black hole rotation, proton decay, or vacuum fluctuations. Some theoretical physicists have proposed that sufficiently advanced civilizations might be able to influence cosmic evolution itself, perhaps by triggering the formation of new pocket universes or manipulating the fundamental constants of physics. These ideas remain highly speculative, but illustrate the profound questions that arise when considering the ultimate fate of intelligence in an evolving cosmos. The story of the Milky Way's future reminds us that our galaxy exists within a much larger cosmic context, subject to forces and processes that operate on scales far exceeding human comprehension. Yet this vast perspective also emphasizes the remarkable nature of our current epoch. When stars shine brightly, planets orbit in stable configurations, and complex chemistry enables the existence of life. We live during a brief but magnificent era in cosmic history, when galaxies actively form stars, when spiral structures trace beautiful patterns across space, and when the universe teems with energy and possibility. The far future may be darker and more quiescent, but it will still bear the imprint of processes we can observe and understand today, ensuring that our scientific exploration of the cosmos provides insights that transcend the boundaries of time itself. In contemplating these vast futures, we gain perspective on our place in the cosmic story and appreciation for the intricate beauty of the universe as it exists today. The Milky Way will continue to evolve, merge, and transform across billions of years, but the fundamental physical laws that govern its behavior will remain constant, connecting our current observations to the deepest structures of reality itself. This has been your trek through the stars. I hope you enjoyed this exploration of the Milky Way and the many wonders it contains. May the cosmos always bring you peace and wonder wherever you are. Until next time, my friends.